This poster is brought to you from the Universidad Complutense de Madrid and the Instituto Superior Técnico de Lisboa, and it is part of the April APS 2022 meeting in New York. Quarks and gluons are almost massless particles. They, however, acquire inertia due to interaction, which gives most of the atoms and our mass. The equations that yield this mass, however, may have more than one solution. This leads to replica vacua that the Lisbon group has been studying for a few years. In this contribution, we employ a variation of the North Carolina model of Coulomb-gauge QCD with a longitudinal Cornell Coulomb plus linear potential and a transverse gluon-induced interaction. The toy field theory is treated in BCS approximation, breaking chiral symmetry and giving quarks a constituent mass. The wave functions of the Cooper pairs solve the gap equation that minimizes the Hamiltonian variation. Depending on the strength of the interaction, it can have several solutions or false vacua, the replicae. The ground state BCS vacuum is at the bottom of the effective potential. Here, the vacuum expectation value of the Hamiltonian. We have calculated the Hessian matrix of second derivatives and found that the replicae are saddle points with negative eigenvalues in some directions in function space. In a finite volume, the system can thus relax to the ground state. But in the thermodynamic limit, this does not seem possible, as the replicae vacua and all states built thereupon become orthogonal to the ground state vacuum and its meson and baryon excitations. They become inequivalent representations of the Fock space. The profiles that we obtain as function of quark momentum are similar to those with the harmonic oscillator, a less sophisticated model, but it gives very similar results, and this shows some degree of model independence. Now we can order the replicae, but the amount of chiral symmetry breaking. A quantity that characterizes it is the quark condensate, that sort of counts the number of quark-antiquark pairs per unit volume. The perturbative chirally symmetric vacuum has no such thing, so the condensate just vanishes. The first and second replica vacua have some small absolute values of the condensates, and this is largest for the most deeply bound ground state BCS level. Condensates are, however, not directly observable. We need excitations built over these vacua. These replicae are analogous to collective excitations in nuclei, in which many particle-hole pairs yield a substantial deformation, but the one-particle, one-hole spectrum can be built on top of that. In Hadron physics, a full spectrum of mesons and baryons may be built on top of each of the replicae. So how do we know over which vacuum are we sitting? The left plot shows the spectrum of pseudoscalar and the right one of vector mesons. The magenta column in both shows the experimental meson spectrum. It is clear that perturbative vacuum is in gross disagreement with experiment by having a massive pion around 500 megaelectronvolts. Now, among the ground and excited BCS replicae, the differences are minor. All of them break chiral symmetry, although with different intensity. So all have a massless Goldstone boson pion in the chiral limit, and tuning the quark mass can give the physical pion mass. Whatever differences between these are at the level of the model's imprecisions, but we have found a major difference in the decay constant of the pion, that is an integral over its wave function. As a Goldstone boson, the pion wave function coincides with the Cooper pair wave function that we here discussed. The experimental value for Fpi is about 100 megaelectronvolts. The replicae have only a tiny fraction of that. Only the ground state BCS vacuum comes close, although it falls short of the physical vacuum. Now this is a model deficiency. Zwanziger of New York University famously showed that the potential that we are using to get the spectrum right, the confining potential, needs to be increased to get wave functions precisely. Now we have questions that we would like to be able to answer and would love to hear from you. First is, how do we extract such excited collective vacua in lattice QCD? If we could, then we could bring more precise theory to bear on these replicae. Second, can we excite them in small volumes at colliders? Or third, perhaps, could they have been frozen as orthogonal relics in cosmology, providing observable effects? Well, here is a last plot of our energy surface, once more, with horizontal lines that now give the black body energy density for a pion gas at various temperatures. At 120 MeV, the replicae can be populated, so we think they should be further studied.